flying boats caught here in beautiful formation flight were conceived, designed, and built by the Consolidated Aircraft Corporation, and from their inception were destined to become outstanding patrol bombers of the world. Their load-carrying capacity, their speed, range, and reliability have been amply proven in extended flights, and their striking performance won for their builders the largest order of twin-engine flying boats ever placed. More than 200 of these flying ships were built for the United States Navy. In groups of 12, 14, 18, and even 48, these famous planes, flown in formation by United States naval pilots and consistently adding to already impressive records of mechanical performance, have repeatedly demonstrated their ability to travel distances of from 2,500 to well over 3,000 miles non-stop, a truly remarkable record of flying boat stamina and consistent performance. As we fly along San Diego, California, with its ideal year-round flying weather, landlocked harbor, and municipally owned flying field. This is Lindbergh Field, where the Consolidated Aircraft Corporation is located, the birthplace of the PBYs, as these flying boats are officially known. This manufacturing plant has an area of approximately 750,000 square feet of space devoted to the production of these airplanes. Here in this large engineering department is grouped one of the outstanding engineering forces in the manufacture of aircraft today. It was from this department that the famous PBY flying boat design emanated. It is here that the Consolidated airplanes are conceived and engineered months before they're publicized to be brought carefully, methodically, and painstakingly to perfection, keeping Consolidated in the forefront in the production of the world's finest aircraft. The engineering drawings and specifications are now translated into orders for materials, and the sequence of operations is determined. Meanwhile, the task of tooling up for production is set in motion, with hundreds of skilled tool makers employing the finest machine tools available. A battery of fast-cutting shapers, a jig borer that works to 5/10,000ths of an inch, a pantograph cutter which burns away chunks of metal, and even a 40-foot planer are used in the building of the tools. As the tool room swings into action, so does the large pattern shop. Hundreds of aluminum alloy forms and wood patterns must be made, for each large airplane design requires numerous fine castings, and these airplanes are no exception. Highly trained craftsmen lend their skill as the very groundwork for production begins. Quantities of high-grade raw materials are arriving for use in the building of the airplanes. These are carefully unloaded, checked in at the stockroom, given a thorough inspection, and then dispatched to the various departments for the many processes to be performed before the material as finished parts enters the airplane. Power shears cut their way into the sheet stock, following rapidly the irregular outlines of the templates. Powerful punch presses chunk away at thousands of gussets, clips, and brackets, blanking, piercing, bending, and joggling. Drop hammers pound away, forming deep, irregular shapes as the power hammers smooth the long, graceful streamlines of the airplane's skin covering. Lathes shave away excess material, and a battery of multiple drill presses spiral into part after part, drilling holes for bolts, bearings, bushings, and some of the thousands of rivets that hold the structure together. Drill jigs and fixtures ensure accurate, interchangeable work for the myriad parts. Throughout the entire structure of the flying boat, a fine degree of accuracy in machining and fitting is maintained. This accounts for the smooth, efficient functioning of the PBYs and has made possible the incontestable performance so often demonstrating their stamina. The oil tanks of the flying boats are built as sections of the two-engine nacelles and are fabricated in special steel assembly fixtures. These fixtures are examples of the special tooling necessary in the production of fine aircraft. To ensure that no leaks will occur, the completed tanks are sealed. A small amount of air pressure is introduced and the whole tank immersed underwater. Here, a leak would be detected instantly as a column of bubbles coming to the surface. Before a new tank design is accepted for quantity production, it must prove its ability to withstand excessive loading and severe mechanical vibration. These tests greatly exceed the stresses which will be encountered under actual flying conditions. To make accelerated corrosion tests, a salt spray booth is used. to check the corrosion resistance qualities of metals and finishes. This is only one phase of the chemical testing, which keeps a constant check on all the materials as they are received and processed to ensure that they will measure up to the exacting standards set. In the physical testing laboratory, all manner of testing, from the determination of the tearing qualities of pieces of fabric up to crushing structural specimens in the powerful 200,000-pound hydraulic machine, is carried on. This destructive testing gives the engineers information which is vital to them in their constant effort to reduce weight and at the same time increase the strength of the airplane. Slowly and painstakingly, these specimens are tested to destruction in order that the most efficient designs may be determined. Just watch those meters go up. There she goes, and the engineers have the actual answer to their problem. Into the anodic tanks go all aluminum and aluminum alloy parts for the anodic treatment. This process forms on every surface a protective film of aluminum oxide, a tough, corrosion-resisting basic protection which becomes a part of the metal itself and which makes an excellent base for paint. Inspection plays a highly important part in the production of these record-breaking planes. The inspection department carries on the inspection of every part of the plane, from the raw materials at the very start, straight through each operation, process, and assembly, to the finished PBY as it rolls off the production line. To maintain the highest standard of workmanship, each part and assembly is checked after each manufacturing sequence. Thus, there is built into the plane an insurance for record-breaking performance. Hardness testing machines instantly determine the exact heat-treated qualities of every metal part used in these boats. These machines are both fast and accurate in operation. Micrometers and gauges are used to check fits and tolerances. As a precaution, to ensure that the parts are measured with accurate tools, these checking devices are checked periodically on the supermicrometer, or master checking device. More than a surface inspection is necessary on the important structural parts. The grain of the metal of which these parts are made must be carefully examined for flaws. Visual inspection will, of course, reveal the obvious flaws, but for these highly loaded steel assemblies, it is important to check for defects that can't be seen. To accomplish this, the simple magnaflux method is used. First, the steel part is magnetized. Then, it is placed in an agitated solution of light oil containing powdered iron. After a brief immersion in this solution, the part is removed, and all flaws, even those ordinarily invisible to the naked eye, will be clearly marked with a dark streak. Thus, Consolidated builds into each airplane structure the ability to take rough handling from either man or the elements, plowing and smashing into rough water at high speed, bouncing and shaking under the impacts, but emerging each time staunch and ready for more, without a sign of the pounding it has taken. In the welding department, hundreds of steel parts are joined together under the flaming needles of expert welders. Under their skillful hands, the steel melts and flows to fuse separate parts into single pieces of exceptional strength. Strong steel tubes welded together form the engine mounts which harness the 1,000 or more horsepower packed into each one of the PBY's twin engines, and each engine mount has plenty of strength to spare. Approximately 900 feet of tubing is used in the PBY. It curves in and about the structure of the airplane, supplying fuel and oil, providing a conduit shield for the intricate electrical nerves of the ship and for the fire extinguisher lines, de-icer equipment, and various instruments. The tube benders have perfected their art to a science. They just put the tube in the bending machine, clamp it securely, give it a pull, and it is shaped. Spot welding fastens together non-structural members which are not called upon to carry heavy loads. An electrical current passing between the two electrodes fuses or spots the two surfaces together by a quick, clean method, as with this segment of the engine cowl flap assembly. These automatic rivet-making machines, cutting steadily away at coils of dural wire, biting off exact lengths, upsetting the heads, and repeating, can turn out as many as 1,000,000 rivets a week. 1,000,000 rivets per week. Emerging from the machines, the rivets are placed in the heat treat furnace for a timed period, and as they leave the furnace, they are automatically quenched in cold water. When they are subjected to this treatment, they become relatively soft and are in proper condition for use. Taken from the automatic heat treating machine, they are stored under low temperature in a large electric refrigerator where they will remain soft indefinitely. If the rivets are exposed to normal temperatures, they soon become hard and develop their full strength. To make them more accessible to the workmen, they are distributed to smaller electric refrigerators located throughout the factory. As needed, the rivets are taken from the refrigerators located adjacent to the work and riveted into place. Within a few hours, the rivets harden and contribute their full strength to the airplane structure. To form the long sections of channels and other shapes used in the construction of the PBY airplanes, the drawbench machine is used. Pulling a strip of dural first through an oil bath to lubricate it, and then through a series of rolls that gradually shape up the desired section, the drawbench gives shape to flat strip stock which, when formed, becomes important structural members. Under process in this drawbench machine is a box-like section resembling a square tube open on one side, which is used extensively in the wing trailing edge and movable control surfaces. Steel tubing of heavy gauge is run between three powerful rolls to form the engine mount ring. Straight to begin with, the steel tubing is given a slight curvature on the first pass through the machine. Then, each time it is passed between the rolls are tightened a bit more until the desired curvature is secured. Kinking of the tubing is thus prevented, and the tube emerges finally smooth and of the exact radius desired. For extruded and drawn shapes, the pneumatic wiping machine is used, which, with remarkable speed, wipes the extrusion to a curved form. Here, for instance, is an extruded section to hold the plexiglass for the landing lights in the leading edge of the wing, formed in a few seconds. Most of the metal parts of the planes are formed in the soft or annealed state and must be heat-treated to gain their full strength. Soft aluminum alloy parts are soaked in a gas-fired molten salt bath, then removed and quenched in water. When quenched, these parts air-harden to develop their full strength within a few hours. Steel parts, according to their composition and ultimate use, receive various heat treatments. Some are quenched in oil. All heat treating is kept under accurate control by a battery of automatic recording pyrometers to ensure the uniform results. The steel tube engine mounts are heated in gas-fired furnaces, and when removed are immediately bolted to a rigid table for air quenching. Bolting the work down during cooling prevents the mounts from warping out of shape. In the plating department, a multitude of small parts of steel, brass, and bronze are given a protective coating of cadmium plate, which protects the basic metal against contact with salt air and the corrosive action of seawater. In the bench department, ribs for the trailing edge of the wing center are made. Here, the box-like section we saw a moment ago, coming from the drawbench machine, is being used in the making of the ribs which are riveted up in the trailing edge assembly fixture. Thousands of small parts are fabricated in the bench department and made into assemblies and sub-assemblies. An interesting material used in the PBYs is plexiglass, a clear plastic material which becomes pliable when heated. The pieces here being formed are coverings for the landing lights, which are located in the leading edge of the wing. To form the plexiglass and give it the desired shape, it is first heated, then placed between two felt-covered forms and held in shape till it cools. When it is cooled to normal temperature, it becomes hard and tough, yet remains perfectly transparent. For launching these airplanes and beaching them, a beaching gear is provided. The gear, which is equipped with brakes, can be stowed aboard when desired and has large pneumatic tires to permit handling the airplane on a sandy beach if necessary. Thus, the PBY can operate to and from temporary bases with ease. In the bench department, too, the control yoke with control wheels for the pilot and co-pilot are assembled and connected up with the control cables. Each cable used in the airplane is stretched and proof-loaded on a cable-proofing machine. This machine takes all stretch out of the cables before installation and overloads them to several times the maximum strain they will be subjected to under actual flight conditions. This loading amounts to 60% of their ultimate strength, and they are held at this load for a period of 3 minutes. Then, having proven beyond all doubt that they are of ample strength to meet the requirements, they are ready for installation. This is the stabilizer unit in the process of assembly. It approaches more nearly its familiar appearance after covering and the fin and stabilizer tips have been added to the unit. The rudders are assembled and riveted up in a vertical jig, and the wing trailing edges for the center section are likewise assembled in the vertical position. All movable control surfaces and the trailing edges of the wings are fabric covered. The cloth used for this purpose is a light, strong, uniform grade of unbleached long staple cotton, and attachment to the surface is accomplished by stitching a reinforcing tape over each rib. A knotted stitch is used which cannot become untied, and which serves to evenly distribute the loads and likewise prevent chafing, wearing, or ballooning of the fabric. Hand sewing using a strong waxed thread is employed in closing up the control surfaces or to fit around an irregular shape where machine sewing is impractical. By using this method, the fabric is pulled uniformly snug over every portion of the surface. The PBY spars are the main structural members within the wings and are assembled in special jigs. The webbing, aluminum alloy extrusions, fittings, and all other appurtenances produced by the various departments are assembled here. The work accomplished in these assembly fixtures encompasses all of the necessary assembly operations except riveting. Before riveting, the spar is disassembled, sent to the paint department to be anodized and primed. Upon its return, it is reassembled. Screws are used to hold the assembly together temporarily while the rivets are inserted and driven. Cleaned, painted, and riveted, the spars are now complete. From above the wing center section assembly line, some idea of the scope of operations in the building of these units can be gleaned. This part of the plant is devoted exclusively to the assembly of the wing center sections. The leading edges, trailing edges, outer panels, and ailerons are assembled elsewhere. These wing center sections are built in steel assembly fixtures which hold the work in a vertical position so that a number of men can work in a comfortable standing position both on the upper and lower surfaces of the wing at the same time. First placed in the assembly fixture is the rear spar, which is guided into position and made fast in the jig. Then come the wing ribs and bulkheads to give the wing its shape. The bulkheads also form a portion of the built-in fuel tanks. When all are in place, the front wing beam is brought to the assembly fixture and raised with pneumatic hoists to its position at the top of the fixture. The fuel tanks of the PBY, having a combined capacity of 1,750 gallons, are actually built as an integral section of the wing structure, a design feature that has several outstanding advantages, one of these being that only a portion of the weight necessary for separately built tanks is required. Although the original airplanes of this type established several distance flight records, the standard production PBYs have attained an unequaled reputation for non-stop mass flights over long distances so repeatedly that they are no longer front-page news, but are proof of the progressive engineering built into each consolidated airplane. The wing center section, weighing approximately 1 ton at this stage of assembly, is raised out of the assembly fixture and is transported overhead by monorail to another portion of the assembly line. The 2 black dots in the center of this portion of the wing are manholes which permit access to the interior of the fuel tanks. The men may thus work inside the tanks and complete the assembly operations. These manholes also permit making inspections in the fuel compartments during service. Arriving at its allotted place on the assembly line, the center section is lowered and rolled to a horizontal position so that the remaining assembly operations can be completed. Immediately after the wing center section is leveled, the sub-assembled parts of the engine nacelle structure are brought to the front of the wing assembly and the work of their attachment begins. Slid into place and held firmly with locating fixtures, the attachment of the nacelle braces and preformed skin is made directly to the front spar and center section skin, so that the nacelles become a part of the wing itself. Then follows the operation of fitting the leading edges to the wing center section. Inasmuch as all leading edges and trailing edge sections are completely detachable, drill jigs are used, so that replacements may be made with ease in the future life of the boat should the occasion arise. Upon completion of the engine nacelle structure, the fuel tanks and related work on the wing, the tanks are sealed and tested under an air pressure of 3 pounds per square inch. A soap and water solution is used over all the tank portion of the wing in a thorough test for gas tightness. By employing this procedure, any leaks which might be present are instantly detected, clearly marked, and the proper means taken to eliminate them. The operations on the wing having been completed, it is now rolled out and heads for the finishing and final assembly department. Meanwhile, the belt frames and bulkheads of the hull are taking shape. The belt frames are the intermediate formers, while the bulkheads are the main formers. The bulkheads, besides giving form to the hull, also serve to divide it into watertight compartments so that the airplane becomes a truly seaworthy boat when on the water, and like a surface vessel, is fully capable of coping with any emergency. The building of the belt frames and bulkheads progresses in much the same manner as the building of the spar assemblies. The smaller parts, made elsewhere in the plant, are brought to the assembly fixtures, placed, secured in position, and drilled. Then, held together with screws, the entire assembly is lifted from the fixture and the riveting operations carried out. When the two major bulkheads have been fastened together with screws, they are raised to the vertical fixtures where the workmen may carry on 2 tiers deep the drilling and fitting operations. These are the 2 bulkheads which attach directly to the wing and the wing lift struts. They also form the backbone of the superstructure. With the bulkheads and belt frames completed, the first operation in the assembly of the hull begins. Finished bulkheads and belt frames are lowered into the large assembly fixtures, bottom side up, for the first work in the fabrication of the hull is accomplished while it is resting in the upside-down position. Many of these upside-down assembly fixtures stand side by side on the assembly floor, and in the inverted position, the long, graceful lines of the PBY design begin to form as the belt frames, bulkheads, and keel sections find their places and the bottom stringers are added. Plating the hull bottom comes next. To ensure a watertight union between the stringers and the bottom plating, a strip of fabric impregnated with marine glue is laid over the stringers before the skin is applied. To draw the plates down tightly against the stringers while the riveting is carried out, small wooden wedges are used. With the bottom practically completed, the growing hull with temporary truss work to prevent its buckling is raised from the upside-down assembly fixture, rolled to a right-side-up position, and moved to a waiting fixture on the right-side-up assembly line. At this juncture, an excellent idea of the interior construction of the hull may be gained. Notice that these bulkheads divide the hull into 5 watertight compartments, so that these boats can battle against inclement weather in the air or ride out bad storms on the surface of the sea. In the right side up assembly fixtures, the upper form of the hull develops rapidly as stringers on the sides and deck are fitted into place. After the stringers have been made fast to the bulkheads and belt frames, the skin is riveted to the structure. Up forward, the cockpit enclosure, an assembly of windows and framework, is brought to the ship and fastened to the growing hull above the pilot's compartment. Aft, the fins are built integrally with the upper portion of the hull and are fared into it. Up on the fin, high above the waterline, providing ample clearance for handling on rough water, will rest the full cantilever stabilizing and control surfaces. From these control surfaces, the steel control cables are brought inside the fin and on down through the hull, away from all spray. The anchor stowage box, anchor winch, nose bumper, snubbing post, mooring walks, and similar surface boat equipment, all material aids in mooring, anchoring, and beaching the craft, are built into the bow. Above the hull in the superstructure, the flight mechanic's station takes form. From here, the mechanic will regulate the retractable floats, the majority of the engine controls, and check the engine instruments, thus relieving the pilot to some extent in the handling of this giant craft. Nearing completion on the assembly line, the graceful hulls are lifted out of their assembly fixtures. The fin, superstructure, pilot's enclosure, turret, and hatches have been secured in place, and the hull is ready for watertight testing. The hull is supported on a stout framework, the water poured into each compartment, and the outside of the hull inspected for leakage. As we look down on the assembly line, we gain some idea of the multiplicity of operations necessary in building of hulls for these famous boats. In the foreground, the hulls are but bare skeletons consisting of bulkheads and keels in their upside-down fixtures. The stringers have been added to some, the plating to others. Along the line on the right side up fixtures are stringers on side and deck. Some have plating with sub-assemblies added. Farthest along, the hulls, virtually finished at this stage of the assembly, lack only last-minute additions to their structure and the watertight testing operation before they are ready to leave the department. Immediately following assembly, the hulls are moved to the finishing department and stripped of the priming coat which has served for protection during assembly. This primer is removed down to the metal, but this does not, of course, affect the anodic film protection which was made a part of the metal itself when the material was anodized. After the primer is removed, the hull is washed and rinsed, and then a fresh coat of primer applied so that the base upon which the subsequent finishing coats are applied will be as near perfect as is possible. The wing center section structure likewise receives the same careful treatment when it enters the finishing department. In the finishing department, the application of paint and lacquers is conducted under ideal working conditions. Warmed and filtered air is forced into this department by huge blowers, and a constant positive pressure is maintained so that no foreign matter can gain entrance. Scrupulous cleanliness prevails with all lacquer dust and paint fumes sucked from the paint booths by powerful fans. Such precautions before and during painting ensure that the finish will be of the highest quality and afford the greatest protection possible. Clear airplane dope is applied to the fabric-covered control surfaces, the ailerons and wing trailing edges, to pull the fabric taut and add strength to the unit. Tape is doped over the reinforcing tape previously applied over all ribs to ensure maximum strength and smoothness. To facilitate the operation, work of routine inspection and servicing of the airplanes, pertinent instructions and markings are applied to the finished surfaces with decalcomania transfers. These are applied tacky and the paper backing washed off. As the hulls are turned out by the finishing department, they are moved to another section of the plant devoted entirely to final assembly operations. Rolling easily on its beaching gear to its allotted place in the line, the hull is now ready for its wings, engines, and tail surfaces. Through the central portion of the leading edge between the two nacelles run a maze of wires, conduits, and tubes. These lead the instrument and control lines to the flight mechanic and pilot, placing within their reach the controlling factors of efficient engine operation. The wing center section, built for interchangeability and perfect alignment, is brought to the hull and gently lowered onto the superstructure. As it is maneuvered into alignment, the sturdy attachment bolts are slipped home and the lift struts are attached, holding this portion of the wing securely in place. Brought to the stern of the ship are the tail surface units to be mounted high on the fin. The engines, after being cleaned of their storage oil and grease, are washed down, flushed, and drained. Then, attached to their steel engine mounts and supported on assembly bucks, the engine accessories are added. These accessories include starters, generators, carburetors, exhaust gas collector rings, preheaters, ring cowls and cowl flaps, as well as propeller governors, oil, gasoline, and instrument lines, together with the necessary clips and control linkages. Thus assembled, the power plant units are hoisted up and transported by monorail to the waiting airplane, where they are swung into position for attaching directly to the oil tanks at the nacelles with 4 stout bolts. These twin double-row 14-cylinder power plants generate well over 1,000 horsepower each and enable the PBY on one engine alone to maintain full flight with full load. More remarkable, however, is the ability of this same ship not only to take off with one engine, but to sustain flight with sufficient fuel aboard to fly 1,300 miles. The weather which prevails at San Diego the year round is ideal for the completion of many of the final assembly operations out of doors. The nearly completed ships are wheeled out and signaled to their positions in the paved yard. Work platforms are shifted into place and final assembly operations are continued. Constant speed propellers, which automatically meet changing conditions and increase the flying efficiency of the airplane, are hoisted to the engines and slipped on the propeller shafts. The outer panels of the wing are brought to the center panel which we followed through construction and are attached. These outer panels contain the wing tip floats, and with the integral fuel tanks of the center section, constant speed propellers and other features contribute to the outstanding performance records of this airplane. As the plane's near completion, United States Navy insignias, numbers, and squadron emblems are added on the hull, the wings, and the tail surfaces for identification. These boats are used by the Navy for bombing, scouting, and patrol work. Flying far at sea, these PBYs can maintain close or open formation as many have done repeatedly in the establishment of the massed flight records, or they can be flown on individual missions. Powerful radios permit constant communication with each other or with shore stations. Contributing to the efficiency of the PBYs are the retractable wingtip floats, which, when the airplane is flying, are retracted into the wing to reduce drag. When down, they serve as air brakes in the approach for a landing, and in addition provide wingtip buoyancy for maneuvering on the surface of protected waters or in the open sea. The PBY design is not only an aeroplane of outstanding merit, but when on the water is a boat fully capable of coping with any open sea contingency that might be encountered during its operation. The controls are now given a first inspection to see that they are functioning smoothly. The ship is fueled in preparation for starting the engines on their initial 15-minute shakedown run-in. Then, following a second inspection and checking of all the controls and instruments, the engines are given a second run-in of 45 minutes to ensure perfect function. After a final checkup, the plane is ready to leave the plant. The PBY flying boat is the culmination of many years of continuous development and research in flying boat design by the Consolidated Aircraft Corporation. And this plane, soon after its introduction, became the world's outstanding surface patrol bomber flying boat. The first of the production PBYs were finished late in 1936, and early in 1937, several records for patrol boat flying were shattered by these ships. Following this outstanding airplane through its manufacturing sequences naturally kindles a desire to see the compact interior of the completed ship as the pilot and his crew see it. This is afforded by a trip through a commercial version of the PBY owned by Mr. Richard Archbold of the American Museum of Natural History. Inside the bow compartment of the Archbold plane, looking forward, may be seen on the left the anchor winch box, and on the right the anchor secured for flying. The black object in the upper center is an electrically controlled aerial camera. Below it, a covered window which may be opened for observation of the camera's field. The pilot's compartment is next, with the control yoke with its dual control wheels, duplicate flying instruments, automatic gyro pilot, complete visual signal system, interphone communicating system, throttles, and constant speed propeller controls. Next is the compartment for the navigator and radio operator. Here, looking forward, we see the navigator's table on the left, and the radio operator station with its two transmitters on the right. Visible also is one of the watertight doors. Fresh water tanks and interphone equipment may be seen, and here's Mr. Archbold in the radio and navigator's compartment. In the mid-compartment of this flying boat were built large cargo platforms with removable seats so that bulky supplies could be transported during exploration work in New Guinea. The flight mechanic's station takes up none of this cargo or passenger space, as he is located above in the superstructure. Up here, he watches over the engine instruments and makes necessary adjustments to most of the engine controls, thus relieving the pilot of this phase of the plane's handling. He receives his orders from the pilot by interphone or by the visual signal system. Amidship is the main cargo or living compartment, which has ample room for a variety of arrangements for carrying freight or passengers. Next, aft, is the rear entrance compartment, which is also the galley of the ship. This compartment contains a 16-foot collapsible boat, washstand, and 3-burner stove. A flying ship on long hops, like a surface ship, is not complete without a galley for the preparation of meals. The last compartment is the tunnel compartment. On the right and left are landing flares, and in the center the watertight hatch through which Archbold drops supplies to jungle parties while in flight. The PBY design lends itself admirably to regular airline flying boat operation, since the interior can be arranged for the seating of some 24 passengers on a day run. For a night run on scheduled service, it can be arranged for the accommodation of 12 berths. From the plant, where the personnel, facilities, and machinery for the building of the most modern aircraft are equal to those to be found any place in the world, have come the PBYs, a product exemplifying the continual progress that keeps Consolidated in the vanguard. Delivery operations always attract interest, as the planes are made ready on the ramp for their first taste of the waters of the bay, and a delivery, in this case, to the United States Navy. The full Navy crew, accepting delivery of the PBY, and Consolidated's chief test pilot, Bill Wheatley, climb aboard. In a moment, Wheatley arrives up forward. The Navy pilot signals the flight mechanic to turn over the engines while Bill peers out to watch the familiar operation. The Navy operators find the engines take hold easily and begin their run-in for the warming-up operation before they signal their readiness to enter the water and the actual delivery takes place. Of the engine controls, the pilot is concerned only with the throttles and propeller governors. The flight mechanic handles the starting, mixture control, fuel flow, engine cowl flap regulation, and so forth. He also controls the raising and lowering of the floats, receiving his orders from the pilot by means of the visual signal system or the interphone. The beaching gear enables the PBY to be handled with ease on land. It can even operate from a sand beach, and the gear can be removed and stowed aboard with ease. Probably in no other spot in the world could the conditions be so perfectly suited to the manufacture of aircraft as here at San Diego, the home of the Consolidated Aircraft Corporation, where fine flying weather prevails throughout virtually the entire year. The Consolidated Aircraft plant is situated adjacent to the land-protected harbor of some 22 square miles, with the harbor providing an ideal flying field for boats and the ocean outside the harbor ample rough water proving grounds. Rail and steamship lines connecting with every port in the world come to the very threshold of the plant. A familiar sight on the Bay of San Diego has been the takeoffs of the PBYs, starting the long-distance non-stop mass flights which demonstrated their outstanding performance. So far as is known, the PBY, designed and built by Consolidated, is the only twin-engine flying boat which has actually taken off from the water with one motor completely stopped. Not only has the PBY achieved this feat, but it has actually taken off on one motor with sufficient fuel aboard for a non-stop flight of 1,300 miles. An unparalleled demonstration of reserve power. Is it any wonder that these remarkable records have been achieved? The following outstanding flights were made during 1937 and 38. Youthful leader of the scientific expedition of the American Museum of Natural History, chose the PBY type as the backbone of his expedition. While the expedition to distant Dutch New Guinea was being arranged, Archbold and his flying explorers calmly assembled last-minute supplies and made arrangements for 2 years of operations over unexplored tropical jungles more than 7,100 miles from San Diego. New and startling are the uses to which Richard Archbold put his airplane. Most of the expedition's flying is entirely over land. Equipment and personnel were transported into the very heart of an otherwise impenetrable jungle to establish base camps on lakes and rivers, and supplies were easily dropped from the plane to exploring ground compartments. Airplanes equipped as patrol bombers for the United States Navy are fast and powerful. They have extended the protective area far out to sea from existing air bases, completely blanketing the United States in a patrol area of 60 million square miles, an area covering 1/3 of the Earth's surface. Beyond comparison with any contemporary service type, the Consolidated designed and built PBYs have amazing flexibility. They are completely seaworthy, possess a range in excess of 4,000 miles, and remarkable stamina under all conditions. An outstanding achievement in themselves, these twin-engine flying boats suggest the future potentialities that will emerge from the combined engineering progressiveness, facilities for manufacture, and the building skill of the Consolidated Aircraft Corporation. Destructive testing gives the engineers information which is vital to them in their constant effort to reduce weight and at the same time increase the strength of the airplane. Slowly and painstakingly, these specimens are tested to destruction in order that the most efficient designs may be determined. Just watch those meters go up. There she goes, and the engineers have the actual answer to their problem. Into the anodic tanks go all aluminum and aluminum alloy parts for the anodic treatment. This process forms on every surface a protective film of aluminum oxide, a tough, corrosion-resisting basic protection which becomes a part of the metal itself and which makes an excellent base for paint. Inspection plays a highly important part in the production of these record-breaking planes. The inspection department carries on the inspection of every part of the plane, from the raw materials at the very start, straight through each operation, process, and assembly, to the finished PBY as it rolls off the production line. To maintain the highest standard of workmanship, each part and assembly is checked after each manufacturing sequence. Thus, there is built into the plane an insurance for record-breaking performance. Hardness testing machines instantly determine the exact heat-treated qualities of every metal part used in these boats. These machines are both fast and accurate in operation. Micrometers and gauges are used to check fits and tolerances. Twin-engine flying boats caught here in beautiful formation flight were conceived, designed, and built by the Consolidated Aircraft Corporation, and from their inception were destined to become outstanding patrol bombers of the world. Their load-carrying capacity, their speed, range, and reliability have been amply proven in extended flights, and their striking performance won for their builders the largest order of twin-engine flying boats ever placed. More than 200 of these flying ships were built for the United States Navy. In groups of 12, 14, 18, and even 48, these famous planes, flown in formation by United States naval pilots and consistently adding to already impressive records of mechanical performance, have repeatedly demonstrated their ability to travel distances of from 2,500 to well over 3,000 miles non-stop, a truly remarkable record of flying boat stamina and consistent performance. As we fly along San Diego, California, with its ideal year-round flying weather and their stamina. The oil tanks of the flying boats are built as sections of the two-engine nacelles and are fabricated in special steel assembly fixtures. These fixtures are examples of the special tooling necessary in the production of fine aircraft. To ensure that no leaks will occur, the completed tanks are sealed. A small amount of air pressure is introduced and the whole tank immersed under water. Here, a leak would be detected instantly as a column of bubbles coming to the surface. Before a new tank design is accepted for quantity production, it must prove its ability to withstand excessive loading and severe mechanical vibration. These tests greatly exceed the stresses which will be encountered under actual flying conditions. To make accelerated corrosion tests, a salt spray booth is used to check the corrosion resistance qualities of metals and finishes. This is only one phase of the chemical testing, which keeps a constant check on all the materials as they are received and processed to ensure that they will measure up to the exacting standards set. In the physical testing laboratory, all manner of testing, from the determination of the tearing qualities of pieces of fabric up to crushing structural specimens in the powerful 200,000-pound hydraulic machine, is carried on. For each large airplane design requires numerous fine castings, and these airplanes are no exception. Highly trained craftsmen lend their skill as the very groundwork for production begins. Quantities of high-grade raw materials are arriving for use in the building of the airplanes. These are carefully unloaded, checked in at the stockroom, given a thorough inspection, and then dispatched to the various departments for the many processes to be performed before the material as finished parts enters the airplane. Power shears cut their way into the sheet stock, following rapidly the irregular outlines of the templates. Powerful punch presses chunk away at thousands of gussets, clips, and brackets, blanking, piercing, bending, and joggling. Drop hammers pound away, forming deep, irregular shapes as the power hammers smooth the long, graceful streamlines of the airplane's skin covering. Lathes shave away excess material, and a battery of multiple drill presses spiral into part after part, drilling holes for bolts, bearings, bushings, and some of the thousands of rivets that hold the structure together. Drill jigs and fixtures ensure accurate, interchangeable work for the myriad parts. Throughout the entire structure of the flying boat, a fine degree of accuracy in machining and fitting is maintained. This accounts for the smooth, efficient functioning of the PBYs and has made possible the incontestable performance so often demonstrating landlocked harbor and municipally owned flying field. This is Lindbergh Field, where the Consolidated Aircraft Corporation is located, the birthplace of the PBYs as these flying boats are officially known. This manufacturing plant has an area of approximately 750,000 square feet of space devoted to the production of these airplanes. Here in this large engineering department is grouped one of the outstanding engineering forces in the manufacture of aircraft today. It was from this department that the famous PBY flying boat design emanated. It is here that the consolidated airplanes are conceived and engineered months before they're publicized to be brought carefully, methodically, and painstakingly to perfection, keeping Consolidated in the forefront in the production of the world's finest aircraft. The engineering drawings and specifications are now translated into orders for materials, and the sequence of operations is determined. Meanwhile, the task of tooling up for production is set in motion, with hundreds of skilled toolmakers employing the finest machine tools available. A battery of fast-cutting shapers, a jig borer that works to 5/10,000ths of an inch, a pantograph cutter which burns away chunks of metal, and even a 40-foot planer are used in the building of the tools. As the tool room swings into action, so does the large pattern shop. Hundreds of aluminum alloy forms and wood patterns must be made.